In this video, we're taking a look at vertical circular motion. And vertical circular motion simply means that the object is moving in a circle where the plane of the circle is in the vertical dimension. Now we have two basic cases whenever you're considering vertical circular motion. One case, let's just use the roller coaster as an example. One case is going to be when the roller coaster is going over the top of the circle. And it doesn't have to be a roller coaster. This could be a car driving over a hill. And then the other case is when the roller coaster is on the inside of a loop as it goes around a vertical circle. And so you can come out of your seat whenever you're going too fast over the top, and you can come out of your seat if you're going too slow when moving in the circle on a loop. Okay, so our two limiting cases, if you will, are going to be one, when you're inside the circle. And what this means is that there is a minimum speed required to stay in the circle. What that implies is that you can never really go too fast within reason. You don't want to, damage the track, or if it's whirling a ball on a string where the string breaks, but keeping it within normal limits. That means you can't really go too fast. However, if you go too slow, it should be obvious that you don't stay in the circle, and at some point you're going to fall out of it. The chief example of this is going to be a roller coaster doing a loop. The second limiting case is going to be when you're on the outside of the circle. And what this implies is that there's a maximum speed required to stay in the circle. Now, the best example to use here would be a car driving over a hill. And the reason I use a car driving over a hill is because if the car is driving too fast, it becomes obvious that the car loses contact with the road. With a roller coaster, that's not the case, because a roller coaster, it's got wheels on the top side of the track and the bottom side of the track and the side of the track, which keeps the roller coaster on the track. So with a roller coaster, it's possible to actually go faster than that maximum speed. So this maximum speed that I'm referring to has to do with items which are not physically confined to that circle because of something else. Okay, so that's pretty much it for vertical circular motion. All we have to do now is pay attention to the problem-solving process that was established in the prior two videos. So let's take a look at an example. Okay, so in this example we have an airplane, a fighter pilot who's flying his plane down towards the ground, and he's going to pull out of the dive into a circle. And what we want to know is what the minimum size of that circle, the radius of the circle, has to be so that the pilot never feels a force that's more than 4 times his weight at the bottom of the circle. Now, what we have to be careful with is we're using language that you're not familiar with in terms of identifying various forces. So let's first draw our FBD. It's pretty much always the first step in this process. So we have a pilot who's diving, and then he comes out of that into a circle. And we're looking at this point right here on the circle. So when we draw our FBD, we ask ourselves, what is touching the pilot? And there's only one thing touching the pilot, which means there's a maximum of 3 possible forces acting on the pilot. One must always exist. That's the force of contact. It's going to be the normal force, and it will point straight up. Then we have another possibility with friction, but in this case we don't have to consider friction. And so we're just going to have the only other non-contact force acting on the pilot, which is the force of gravity pointing straight down. So this is going to be a side view FBD instead of a top view FBD. Okay, so step 2 of our problem solving process is to write F net is equal to ma. We ask ourselves, is it equilibrium or non? And of course this is going to be non-equilibrium because we're constantly changing direction. And then looking at the FBD, I substitute for step 3 my forces into F net. Now I've only got 2 forces here, so that's all I'm able to get into F net. If I want to include a third force, I need to be able to justify that force on my FBD. So for F net, we're just going to write the normal force minus the force of gravity is equal to ma. Now, keep in mind that the reason the normal force is positive is not because it points up. It's because it points towards the center of the circle. So that makes the normal force centripetal, or positive towards the center. The force of gravity points away from the center of the circle, which happens to be down, which we normally call the negative direction. But remember, we're not using the XY coordinate system, we're using an RTZ coordinate system. And so this is away from the center of the circle, which is how we justify the negative direction for gravity. That's not always going to be the case. And the acceleration points in the positive direction because it's pointing towards the center of the circle. Now this is where we have to be a little careful, because there's some language that you have to translate into physics language. And if we go back to our question, it says, what is the minimum radius of the circle, so the force the pilot feels? This is key right here. What does the pilot feel? Okay, and it never exceeds 4 times his weight at the bottom of the circle. So what does the pilot feel looking at our forces? We've got the normal force, the force due to gravity, and that's it. So what the pilot feels has to be one of these two. Is it normal or is it gravity? Well, the answer to that question is going to be the normal force. It's always the normal force is what we feel. We actually cannot feel the force due to gravity. If you were to go skydiving, when you first step out of the airplane, you basically feel weightless, yet the force of gravity is still acting on you. The only time you start to feel something is whenever the air is rushing up at you and it's pressing against you. You feel that. When you're standing on the floor, you feel the floor pushing up against your feet, but you do not feel your weight. Okay, so weight is not a force that you can actually feel. Now, the normal force can never exceed 4 times the person's weight. So what we're going to do is we're going to redefine the normal force based on the information given. And we're going to say that the normal force is equal to 4 times the person's weight, or 4 Fg. Okay, so in step 4, we're going to start solving this. And we write 4 Fg minus Fg is equal to ma. So 4 Fg minus Fg is equal to 3 Fg is equal to ma. And a is not one of those quantities that we know, so we have to rewrite it in terms of the quantities we do know. And knowing that acceleration is defined as v squared over r, we're going to write this as m times v squared over r. Now, we don't know the person's weight, and they don't give us his mass. So that's a big clue that we've got to do something to get rid of this mass right here. And the way we're going to do that is by redefining Fg as mg, because we know that Fg is equal to mg. Now, this pilot is near the surface of the Earth. He's not high enough that we should consider using universal gravitation. He's got to be much further away than that. So we're going to write this now as 3 mg is equal to m times v squared over r. The mass cancels out. And now remember, we're solving for the radius, so we're going to get r is equal to v squared over 3g. And then substituting our values for v, we have 230 meters per second, and that's going to be squared divided by 3 times 9.8. So we'll get out our calculator, and we get 230 squared divided by, now be careful because this is a common mistake. Do not do 3 times 9.8. If you do this, what you're really doing is this. In terms of the algebra, you're actually writing 230 squared divided by 3 times 9.8. So you need to make sure that you're putting the correct brackets in, or parentheses, for solving this problem. So it's 2 divided by the quantity of 3 times 9.8. Close our parenthesis, and we get 1799 meters, or 1800 meters. That is 1.8 kilometers. So that is the answer to this question. Now, just for a little bit of additional practice, let's take a look at what happens when this airplane is at the top of a vertical circle. And so we're just going to set up the basic problem. We're not going to solve for anything. So if the pilot is now up here, then what we have is the normal force due to the seat pushing down, and then his weight is also pointing down, the attraction due to the earth. And so now this was step 1, our FBD. Step 2, we write F net is equal to MA. This is non-equilibrium, so this A is going to become V squared over R. And for F net, we're now going to write Fn plus Fg is equal to M times V squared over R. Notice that they are both pointing down, but because we're using the RTZ coordinate system, we take note that this is actually towards the center of the circle, and that is the positive dimension. And so Fn in this case would become 4Fg plus Fg is equal to mv squared over r. And I'm not going to solve this any further because I'm not doing another whole problem. Just be aware that in the RTZ coordinate system, you're always looking for what is towards the center of the circle and what is away from the center of the circle to establish what's positive and what's negative.